Hello everyone, and welcome back to a new video in programming the finite element method using MATLAB. We are approaching the end of solve linear elastic. We finished last time applying the boundary conditions and subdividing our matrices. Today we are going to solve those matrices and as a precursor of doing this stuff. Now, as per usual, I want to mention that this is part of two video series, one of them about the FEM principles and one of them about programming only. Both of them are going to be linked on the top right. Also, I want to mention that my dear channel members have access to the entire source code. However, if you are not a channel members, then worry not, because every single line of code will be written in front of you, so you can write along and you would have the exact same code as mine. So with that being said, and without further ado, sit back, relax, and enjoy this rather short video. Okay. Now, we are going to solve the linear static equations. So, we're going to solve K11, K12, and so on. I want to once again give you a quick reminder of what Daryl and Logan does. Daryl and Logan, in page 42, equation 2.5.14 and 2.5.15, explains to you exactly what the system of equations are that you need to solve and how to solve those. Now, I'm still worried about my equivalent nodal loads. I might have forgotten to add it to the global loads. So I want to investigate this after I finish declaring how I can solve my structure. So this video is going to solve the structure and also is going to check the equivalent nodal loads and if they were applied or not. Because I was spooked in the last video, I thought maybe I forgot to add it to the global loads. So I must make sure that I add it, or I need to explain to myself why I did not add it. The basic system equations is K11 D1 equals F1 minus K12 D2, F2 equals K21 D1 plus K22 D2, the basic system of equations. Now, how do you solve that? Here exists a ton of possible mathematical calculations. Let me show to you very quickly what I do in Strado. In Strado, I have this to offer. This is the stuff that I programmed in Strado. I have the simple matrix inversion. I have the skyline Bater, according to Klaus-Jürgen Bater. I have the Cholesky decomposition, and I have some iterative solvers. Now, the solution of a system of equations, the mathematical techniques behind that, is not part of the series. However, you can check out Klaus-Jürgen Bater and see how the skyline works there. There's an algorithm called the skyline algorithm that solves equations. Now here, I'm going to use the good old MATLAB solution stuff. So I will invert the matrix. This will not be the best way of solving, but it's something I will do nonetheless. So I will go to the simple matrix inversion, and to the basic principle here is I need to find D1, which equals K11 inverse left multiplied by F1 minus K12 D2. Now, the cool thing in my equation is that D2 is 0 because all my boundary conditions are 0. They give a 0 boundary condition. So that's why this can die. And D1 is just K11 inverse F1. So let's do this. I will here go and say object.D1. Now, there might be some errors about multiple degrees of freedom or multiple load cases. I will wait for it. I will call the inverse function. I think it's called inv. Let me check. Random 3 by 3. And now inverse. Okay, let me just say A equals random 3 by 3. And then I'm going to inverse A. So A inverse is going to equal to inverse of A. I think that's the function. And now if I multiply A multiplied by its inverse, I should get the identity matrix. And I get it. So yeah, inverse A is the matrix inverter. I will modify it later if I feel that this is a time sink. But for now, I'll just basically call in the inverse of K11. Oh wait, it's called object.K11. And I will multiply this by the object.F1. Once I have D1, I can find F2 by saying object.F2 equals object. Okay, there's an error here. What's the problem? Object.K21 multiplied by object.d1 plus object.k22 multiplied by object.d2. Now, I don't think this will help because this is usually 0. I'll just keep it for now. Now, this is pretty smart. MATLAB detects and tells you, hey, inversing stuff is bad. How about you can just say A left division B or something? Now, the reason I think is because he will choose the correct algorithm that speeds it up. So I will follow his advice. I will go here and say K11. I will do this. Object.K11 divided by object F1. So that's how he's suggesting it for me. And I will oblige. I gladly oblige. I still think this is slow. It needs to be sped up. But I want to rely on MATLAB and figuring it out first, and then I might add it. So now this ends the solving, but there is still one bug I want to check. The bug I'm trying to check is the equivalent nodal load. Okay, so let's get onto this, because I'm kind of spooked. Let me revisit the apply loads function. So here's the apply loads function, right? We are going into the nodal loads, and we are getting the nodal loads, and then we are applying it to the global load matrix. That's true, by the way. And then for the other loads, we are applying it to the equivalent nodal loads, and that's true. Now, in the end, I should add them together. Did I add them together at the very end of this? Let me make this small, and make this small. Oh my, now this is important. I hope that you don't scroll and just watch me to the end. The thing I'm missing here is at the end of it, I should go to the object, which is the controller, dot global load matrix, and I should add to it the equivalent nodal loads. Object.equivalent. Are you gonna autocomplete? Yeah, that was missing. That was missing, I don't know, 10 videos ago or something. I just realized that I might have messed it up when I was solving, because I have never remembered. I did not remember me adding the loads to the equivalent nodal loads. So in the solver, my error sensors were tingling. And not to tap myself on the back, but this is something called like having a bird's eye view when you program. Okay, so now in the solver, there was a to-do I put somewhere. Let me remove it. I think it was in the boundary condition, right? I put a to-do somewhere to warn myself. I forgot where I put it, to be honest. I remember I put a to-do to warn myself. I think it was here. Yeah, that's the one. So yeah, I checked and I messed it up. So now I have solved it. I have fixed it. So I think now the solve is done. And basically we have achieved another milestone. So yeah, that's everything I wanted to talk about today. I hope you enjoyed. And in the end, I want to give a solver-sized shout out to media channel members in the contributor level and the helper level whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as the support of the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.